everyone. In this video, we will be discussing the first law of thermodynamics, internal energy, and a few other different things. So the first law of thermodynamics is conservation of energy, which means energy cannot be created nor destroyed. The first law can be written like this right here. So we have delta E equals E1 minus E2 equals little delta Q minus little delta W. And it can also be written as the change in internal energy plus kinetic energy plus potential energy. And I wrote kinetic and potential energy going to 0 because in this problem, we are going to say that they are both negligible. Something to note is that big delta E is a property of thermodynamics and a point function, and little delta Q and little delta W are non-properties as well as path functions. And thermodynamic properties or point functions are independent and they don't depend on the path or history. Some examples of this are pressure, volume, internal energy, total energy, enthalpy, and entropy. So our non-thermodynamic properties or path functions, they do depend on path history. And some examples of those are work and heat, which we're dealing with in this problem, mass flow, and entropy transfer, and we'll cover those two in later videos. Before we start this problem, we also need to define our heat engine sign convention and our closed versus open systems. So our heat engine sign convention relates to work and heat being directional, so we need to assign each of them a positive or negative sign. The one thing to keep in mind is that they need to be consistent throughout your entire problem. So for this example, our convention will be heat transfer into the system is positive, as you can see here, and work transfer out is also positive. Over to the right, I listed a more complete set, so it's the opposite for W in and Q out. Next, a closed system is one where no mass can enter or exit the system, and an open system is one where mass can enter or exit the system. So we can see down below, we have our system, and then the kind of squiggly and dashed line right here, that's the boundary, and it has to be 0 for a closed system. So moving on to our problem, we can say water is being heated in a closed pan on top of a range while being stirred by a paddle wheel. During the process, 30 kilojoules of heat is transferred to the water, and 5 kilojoules of heat is lost to the surroundings. The paddle wheel work amounts to 500 Newton meters. Determine the final energy of the system if its initial energy is 12.5 kilojoules. So the first thing we're going to do is write down our knowns and unknowns. So we can say our Q in equals 30 kilojoules. Our Q out equals 5 kilojoules. Our work is 500 Newton meters. The initial internal energy is 12.5 kilojoules. And then we can just mention that we have a closed system. Next, our unknowns. We just have one. It's going to be the final internal energy, so some number of kilojoules. We also need to quickly mention our assumptions for this problem. So like I said before, we have delta kinetic energy, change in potential energy 2, and we're both going to say they're 0 or negligible in this problem. So we don't include them in our first law equation. So now we're trying to find internal energy, which is the amount of energy stored within a system at a given state. So to do this, we can go back to our original equation, which simplified looks a little bit like this. And we can change this to U2 minus U1 equals, we can say Q in plus Q out minus delta W. Now this right here This is our Q total. And so we can get our Q total by saying our heat in, which is plus 30 kilojoules, plus our heat out. And remember our heat engine sign convention, Q in is positive, like I just said here, and then our Q out is negative. So we have 5 kilojoules going out, so it'd be minus 5 kilojoules. So then our Q total is 25 kilojoules. So we also need to get our work into different units. So we were given 500 Newton meters, and we need to convert this into kilojoules. So we can say 1 kilojoule is 1,000 Newton meters. Cancel our units out, and we get half a kilojoule, which is work. Now we're going to plug everything into our equation. So U2 equals 25 kilojoules minus half a kilojoule for work, and then plus 12.5 kilojoules, that's our initial internal energy. So we can finally say that the final internal energy is 37 kilojoules. So the last thing to note is how I said path a lot. And the path of something is just a series of states through a system which passes during a process. And we didn't have many states in this problem, but it'll be helpful to know in the future. All right, I hope you enjoyed this video about the first law of thermodynamics.